So, good morning, everyone. So, thank you all very much for coming. And today we will have Meredith Shea from UC Berkeley, and she will tell us about the generalized Gelfand-Yaglom formula. And in the original version, I believe there was in the discrete and continuous settings. So, please.
Yes, thank you. Yeah, the title gets very long. So this talk is just based off of a paper that I've nearly finished up. I have a few edits before I'll throw it online, so like you can check it out in probably a week. But I guess I'll get started. And yeah, the title is a generalized Gelfand-Yaglom formula, more specifically in the continuous and discrete settings. Okay, there we go. Okay, so just start off with some preliminaries. And ultimately, the first thing I'll do is introduce the usual Gelfand-Yaglom formula. And so what are the preliminaries? Well, we're going to start off with a one-dimensional quantum mechanics system and some potential V. And then so we can write out the action function on the space of paths. It's the usual thing you probably know how to write. And gamma is just a path from the time interval to the space, which in this case is just R, and we denote it by QT. So we're going to specify the classical path or the critical path, whatever you want to call it. And you can use the notation of just a subscript C. And so we have gamma C is equal to QC of T, and this path specifically satisfies the Euler-Lagrange equations. And then we have the specific boundary conditions where we denote QC of 0 to be Q, and then the derivative QC dot at 0 to be P over M. So P and Q are just some parameters, which will change the classical path, I guess. Okay, so what can we do? So the action we had previously, we can take the second variation here at the critical point or the classical path. And so also we're going to throw out the boundary terms when we take the second variation, and we end up with this equation where you have this operator A. It's a second order differential operator, and that's explicit form. And okay, we threw out the boundary terms when we wrote the second variation of the action, but we really hid them in the operator A. So the operator A acts on the domain where we're considering things in the Sobolev space. Basically, the easiest way to think about it is just they're twice differentiable. And then the boundary conditions are y at 0 equals y of t equals 0. So this is our Dirichlet boundary conditions are being considered. Okay, so now we can state the usual Gelfand-Yaglom formula. And so technically what I have written out here is actually like a corollary of it. So what is it? We have A and QC be as described, then the derivative of QC with respect to P at capital T is equal to 1 over 2m times the Zeta regularized determinant of the operator A. And so this is actually proven for more general differential operators that look like minus the Laplacian plus any well-behaved function. Specifically for us, that function is the derivative of the potential we have, the second derivative of the potential we have. So this is proven. I usually reference Takajan to see the proof of this, and it's pretty standard. I'm not going to talk about it because I will prove something very similar and go through a bit of the steps taken there. And the steps are almost identical to the steps you take here. There's just some asymptotic computations that end up changing in the other setting. Okay, so that's the usual Gelfand-Yaglom formula. So now the next step is going to be to define a more general action functional and kind of build from there. So we can rewrite the action functional in terms of the Hamiltonian formalism. And so I'm just denoting it S tilde, it became convention. And so this is just the action written with the Hamiltonian, and then gamma tilde is now a path on the cotangent bundle. And now I also have denoted in like the statement of the action, this Q and Q prime, where they're just the starting and the ending positions of the path. And the reason I denote them is we can think about them like parameters, and we can actually take we can take derivatives of the action with respect to them to get kind of a corollary of the Gelfand-Yaglom formula. And so for the operator A and the action functional described above, we have this alternative Gelfand-Yaglom formula. So where instead of the derivative of the classical path with respect to P, now we have these, the derivatives of the action functional, but it is inversely related. And this is the formula we'll want to build off of. And so to build off of this, we're going to change the action one more time. And so, okay, we're going to consider this even more, which I'm going to call a generalized Hamiltonian action functional. And why is it generalized? It looks basically the same, except I have these two new functions, f1 and f2, which are tacked on at the end. The other difference I'm making is I'm also going to use a general Hamiltonian for now. So in this case, we have any Hamiltonian H that's reasonably well behaved. So probably what I need from it is if it's twice differentiable with P and Q with respect to P and Q. And then what are F1 and F2? So F1 and F2 are going to define some Lagrangian submanifolds. And what are these submanifolds? It's P is equal to the derivative of F1 with respect to Q, and P prime is equal to the derivative of F2 with respect to Q prime. So these are two Lagrangian submanifolds, and we can ask ourselves, well, how does this change like the critical points of the action? The critical points of the action are now going to be flow lines of the Hamiltonian vector field that connect these two submanifolds in the time t. So really what these two Lagrangian submanifolds do is they're just a new type of boundary condition we can consider on the action. But the nice thing is we can explicitly throw it into the action functional here.
Sorry, I'm a little bit confused. Does P prime and Q prime enter the Hamiltonian or anything else except for?
So you can think about Q prime as being a parameter. So it's wherever the path is ending. And so why do we care? Like that, we can think about it in terms of the classical path, like it's just denoting where the path is ending. And so it's going to have to be solutions of like Hamilton's equations. And yeah, you can think about when I write P prime is equal to the derivative of F2 with respect to Q prime here, you can think about them as just like variables in this sense. So the Lagrangian submanifold, you could just consider any value of Q prime, and that's defining the manifold. Okay, so that's the new action functional, and pretty much for the rest of this talk, we're just going to consider this new action in different ways. And then like we were going to do the same exact procedure to it. So before, when we had that other action functional, the first one, we took the second variation and we got this operator A out from it, which was a second order operator that acted on this domain. So we can do the same thing to the new action functional. We can take the second variation and we're going to be left with some operator once we throw out the boundary conditions. And this is the operator. And a side note is I think this slide has really bad notation. So I want to be like a little bit careful here. So when I'm using PC and QC here, these are really, you should think about them as PC of T and QC of T. So so I'm taking derivatives of the Hamiltonian with respect to the classical path here. And that's what these are denoting. They're not like starting or endpoints, they're just derivatives with respect to the path. So obviously this will change with t. And then, so what's the domain now? The domain is a little bit, the boundary conditions are changing, and the boundary conditions change because of those Lagrangian submanifolds we have. And so what we see is that now we have x of 0. So if we imagine a tilde is acting on a vector xy, then x0 is equal to a1 y0 and xt is equal to a2 yt, where a1 and a2 are just shorthand notation I'm using here to denote the second derivatives of f1 and f2 respectively. And the bad notation is really down here. So this should really just be q, and this should really just be q prime, where when I write it like this, I'm thinking about q and q prime as being the specific starting and ending points of the classical path. So these are like, I'm plugging values into these functions. B1 and B2, I've kind of been throwing around and not talked about them yet. B1 and B2 are just parameters that allow us some freedom when creating these Lagrangian submanifolds. And so I have an action, and now I have this operator that arises from the action, and it's different. So before I had the first action S, and then I got this operator A, then I wrote this new action functional S tilde, and I got this new operator A tilde. And so we want a similar formula regarding S tilde and A tilde. Like we want some Gelfand-Yaglom type formula for these two pieces. And the question is like, can we do this? And the answer is sort of. So there's a few steps we took to break it down. We could never answer the question directly, but there's a few steps in the right direction we took. So the first thing we did was discretize everything. In the discrete setting, there are absolutely no issues. We get what we want. The only problem is it's just discrete. So then we kind of turn to the continuous setting, and specifically the Zeta regularization, and ask, can we do this? The Zeta regularization of A tilde is tricky because it's a first order operator instead of a second order operator. So you have a lot of convergence problems when looking at things like contour integrals, but there's no problem when using A. And so in a lot of settings, I can still use the operator A with the new action S tilde. So that's basically what we do in the continuous setting, is look at the relationship between A and S tilde and see what it is. And we edit A slightly, but it's essentially the operator we had before. And the last thing we want to ask is like, what happens in the continuum limit? So does the discrete case make sense in the continuum limit? And also like, can we compare these two? And like, hopefully we want them to be the same or very similar in some sense. And so that's the last question we ask, is what happens in the continuum limit. And what we'll have to do is not just look at A tilde discretize, but we also will have to eventually discretize A, but we won't do that till the last step here. So before I get into the next part, which is going to be all about the discrete setting, are there any questions so far, I guess?
Okay. I'm pretty sure you said this before and I just forgot. What's the motivation again for considering A tilde instead of A?
So A, like, we'll see a couple motivations along the way.
Okay.
One is going to be in the discrete setting, where like A tilde is actually a lot, after doing all the work, A tilde is a lot better of an operator in the discrete setting, especially when you're considering convergence. I think just because it's like A tilde is the natural operator that arises in the Hamiltonian setting, whereas A is more of the natural operator that arises in the Lagrangian setting. The other thing we won't successfully deal with, but was like thought of as maybe a use is in the Hamiltonian setting, it's a lot more general. The operator A, kind of in the Lagrangian setting, is really made for Lagrangians of the form, p squared plus v of q. And if you get beyond that, it gets a lot more complicated.
Okay. Thanks.
Okay, so the next thing to do is discretize the whole thing. So how do we do this? We take a path and we discretize it into n position vectors and n-1 momentum vectors. And so once we do that, we should propose a discrete action functional, which we do. And it looks a lot like our generalized action functional, but the integrals have now become Riemann sums. We're not being careful about epsilon here. We've really set epsilon equal to 1. And eventually when we consider the continuum limit, we'll kind of reintroduce it. But for now, it's just kind of disappeared. We're going to use mostly arbitrary Hamiltonians like before. I guess we want twice differentiable for now. And then Qn here is really Q prime and Q1 is really Q. So it's just the starting and the ending positions. But we get the same, the functions are exactly the same functions F1 and F2 that we saw. And so again, the next thing we need is a discrete version of A tilde. And so we can still take the second variation of this to get a discrete version of A tilde. It's just going to be a reasonably big matrix. So the discrete analog of A tilde, which I call A tilde n, is going to be a 2n minus 1 by 2n minus 1 matrix, and it's got a really useful block form. So I'll denote the blocks of it by D1, D2, D3, and D4. D1 is n minus 1 by n minus 1, and D4 is n by n. It'll be useful to consider this just because when we prove the discrete version of the generalized Gelfand-Yaglom formula, this block form will be useful in part of the proof. So what do these blocks look like? D1 is diagonal, and all the diagonal elements are the second derivatives of the Hamiltonian with respect to each of the PIs. And the same thing basically happens for D4. The only difference is that the first entry in D4 has this A1, which comes from the boundary function F1. And then the last one has a minus A2, which comes from that boundary function A2, but it's still diagonal. And then D2 and D3 are just transposes of one another, and they're not square. They have two non-zero diagonals, I guess. One just contains ones, and the other one has -1 minus the second derivatives. The mixed derivatives appear in D2 and D3, which for a lot of cases we'll consider. We'll kind of assume the mixed derivatives are 0, but we can keep them around generally still. And we also get just like a discrete version of Hamilton's equations, which makes perfect sense. The only weird thing is there's this funny like index thing that happens where P is kind of like lagged. It's like a lag system, I guess. This, I think you probably can get rid of if you choose a slightly different version discrete action functional, but these work just fine too. And again, we have Lagrangian boundary conditions. They're exactly the same as before. And so from this, we're ready to state the discrete Gelfand-Yaglom theorem. Generalized, I guess. So for the discrete action functional at the critical path and discrete Hamilton-Jacobi operator, A tilde n, the following Gelfand-Yaglom type formula holds, and this is just written in the one-dimensional case. And so it looks very similar. Like if you hide this product over here, and you get rid of these derivatives of f, or maybe you just say they're 1 for now, like it looks really like what we had before. And we do expect this to depend on the f1 and f2. That's not surprising. This last term is a bit of a mystery, especially if you try and look at convergence. It is a little funky. But if you consider any Hamiltonian without, mixed terms in it, then you get back what you kind of think. And we also, like in the paper, this is totally written up in any dimension you want. The only thing that changes in this formula is you get a lot of determinants of everything. So like you get the determinant of the derivatives of the action, you get these determinants of the derivatives of F1 and F2 and determinants of this. And the matrices from above, these matrices here, they just become like each of the diagonal terms, for example, in D1 just become their own matrices when you consider multidimensional cases. And so the proof is going to follow the same format in the multidimensional case as well. It's just a lot easier to explain when it's just one dimensional. There's some nuances you don't have to care about, which is quite nice. Okay, so I wanted to give an idea of how to prove this. So for this proof, we do have to assume one important thing, which is 1 plus the mixed derivatives of h are not equal to 0. And we can kind of see where they show up. If they were equal to 0, this product term would just kill everything. So it is a weird case. I don't really know if there's like physical significance to this, but it was the one assumption I couldn't really get around. And then the proof, we have the following steps. So the first thing we want to do is compute the mixed boundary derivatives of the action at the critical value. After just some derivative taking in algebra, it actually simplifies really nicely to this. And so once we get here, the goal is to replace this derivative of q with respect to B2. So to do that, we're going to take Hamilton's equations, the discrete version, and we're going to just take derivatives of them with respect to B2 to get a nice system of equations. So once you take, like, the Hamilton's equations aren't linear, but once you take the derivatives with respect to B2, you get these two linear equations. And you can throw these into a recursive system. And so you have this nice recursive system. It allows you to basically replace this derivative of q with respect to B2. And then the next thing you want to do is consider it from the other end. So we want to consider the determinant of a tilde n. And we can also nicely write this as a recursive system using the fact that, well, as long as D1 is invertible, then we can write out the determinant of a n tilde in the following manner. And in cases where D1 isn't invertible, we can get around it, but it's a longer path around. So it's nicer to just consider this proof in the case where D1 is invertible. And again, for Hamiltonians of the form like p squared minus or plus v of q, we're fine. And so D1 is just diagonal. The determinant's very easy to compute. And then that other funky matrix you have there, D4 minus D3, D1 inverse, D2 is just tridiagonal. And when you have a tridiagonal matrix, you can write the determinant of this as a recursive system, especially because for the most part, the terms are pretty similar. And so it's a pretty nice recursive system. And then kind of the kicker of this whole proof is that these two recursive systems we have are almost the same after a gauge transformation. And when I say almost the same, there's a few differences, and you can probably guess what they are when we have mixed derivatives. So when we have those derivatives of h with respect to p and q, those float around. And also there's a sign difference, which you can also see before. So this term, it's this product term again, which is how they're not the same. If you have no mixed derivatives of h, you still get an alternating sign, which is a little funky. But this is the part that they're not the same with. Okay, and so the same steps apply in the n-dimensional case. there's a few things you have to be careful about, like this matrix, this like product matrix here is now block tridiagonal, but there's still a nice recursive formula for the determinant of a block tridiagonal matrix. And you have to be a little bit careful when writing the systems and recognizing what side you're multiplying on and stuff like that, but nothing hard. So that's how we prove the generalized discrete Gelfand-Yaglom formula. And from here on out, we want to make a few assumptions. So that was like completely general. That worked for basically any twice differentiable Hamiltonian. But the rest of the work we want to do, and kind of relating this back to the continuous case, we really have to make these two assumptions. And the first one is that our Hamiltonian looks like p squared plus v of q. Because in this scenario, I can kind of switch freely between the operator a tilde and the operator a. If I'm not in this scenario, you can't really make that switch happen. The other thing is n is going to be odd when we care about n, I guess, because of that alternating sign. This gives us like the positive convention. And so if we take these two things into account, the statement in the theorem simplifies to the following pretty nice expression. And this looks like very similar to our first Gelfand-Yaglom formula. So I have the inverse relationship. The only difference here is I have these derivatives of f1 and f2 hanging around. Yes, okay. So the next thing we'll want to consider is what happens as n goes to infinity in this expression. And to do this, we will have to consider the matrix a tilde n, and we'll have to consider it with being careful about epsilons, which I never really write out explicitly. But before I start talking about that, are there any questions on the discrete setting and this kind of discrete version of the formula? Okay. So the convergence of a and tilde. If we're careful about epsilons, the operator a tilde n weakly converges to the operator a tilde. And not only does it converge, but we have this, we might want to ask ourselves what happens to the determinant as n goes to infinity. And we can use our discrete generalized Gelfand-Yaglom formula to write out the limit of the determinant in this nice manner. Everything on the right-hand side here is finite and well-defined with an asterisk. So that tells me that the limit of the determinant is also, finite and well-defined. Obviously, I say well-defined with an asterisk because there's this sign, there's this alternating sign that I've just like kind of tossed to the wind because I didn't want to deal with it, which is fine. You just have to pick your convention of what this sign is. But other than that, everything else is totally finite and well-defined. So there's no issues there. So that gives us two things. We have convergence of the operator and this determinant. Like this determinant makes sense in the limit as n goes to infinity. And it's finite, which is, it's actually it's a nice thing to have happen. And kind of the next step here is like, we're hoping that, well, is this in some way equal to or closely related to the Zeta regularization of this operator? Well, which is what I say next. So ideally, what do we want? We want a generalized Gelfand-Yaglom formula for the Zeta regularization of a tilde, because that was like the ultimate goal. And if we have both of these Gelfand-Yaglom formulas, I can compare the Zeta regularization to the limit of this determinant of a and tilde. But the Zeta regularization of a tilde just causes issues. So what do we do instead? We had to think about something else to do instead. So instead, we kind of take a step back and I compute a generalized Gelfand-Yaglom formula for A And so when I say generalized, that means it's going to have these Lagrangian boundary conditions. But it's going to be in terms of the zeta regularized determinant of the operator A, where we amend the boundary conditions on A. So the boundary conditions on the operator A have the following form. They look like mixed boundary conditions, where A1 and A2 are the same A1 and A2 we've had before. So they're the second derivatives of F1 and F2, respectively. And yeah, we just divide by M here because, Q dot is equal to P over M. And so that's what we want to do next. And so we do. We do it slightly more generally, though. And the reason we do it slightly more generally is because that's exactly how the usual Gelfand-Yaglom formula does it. So we let L be the operator, the Laplacian or minus the Laplacian plus U of t, where ut is a C1 function. And then the domain is slightly edited. We still need nice functions here, but the boundary conditions are changing. They're no longer the Dirichlet boundary conditions. And then we get the following theorem. So the zeta regularized determinant of the operator L satisfies the following equation. So the zeta regularized determinant of L is equal to y1, the derivative of y1 at t, minus a2 divided by m times y1 at t, where we need to know what y1 is. And y1 is the solution to the following initial value problem. So it looks very similar to like the operator. It's basically L of y1 is equal to 0, and it has the following boundary conditions. And so the y1 seems unmotivated right now, but I'll try to explain the proof a little, and hopefully why y1 appears here will maybe seem more motivated. Yeah. Are there any questions on that theorem? Before I think the next thing I do is get into the proof of it, which I feel like I have time for. So the proof of this is it follows the original Gelfand-Yaglom formula. Again, the main differences are there's a few computational difference, and then asymptotically it's a bit different. But the proof, the outline goes as follows. I have this differential equation, I guess. Minus y double dot plus u of ty equals lambda y. Lambda is just some parameter. And I'm considering two solutions with the following boundary conditions. So we already saw y1, but we also have this y2, which y2 of t is equal to 1, and y2 dot of t is equal to a2 over m. So if we go back and we look at the domain, y1 and y2 aren't necessarily in the domain of this operator. But if we were able to like kind of stitch them together, then we would get something that works out. So they're kind of like each one is accounting for one of the boundaries. And then obviously solutions are kind of where we magically are able to match them together. So using the two solutions, we're able to simplify the expression, the trace of the resolvent. I should back up as I say this because we do need to think a little bit about our operator L. It's a trace class operator. It's Sturm-Liouville. It's got a nice discrete spectrum that goes off to infinity, and as things get large, the eigenvalues are behaving quite nicely. So we had to use all this information in order to talk about the trace of the resolvent here. But since the operator L is trace class, so is its resolvent, and now we're free to talk about the trace of the resolvent. And we can write the resolvent using these two solutions and one of the variation of parameter, I think, is the method. And then I have this equation that the log determinant is equal to minus the trace. And once I'm able to simplify the trace of the resolvent, I can, this is a typo here. There should be, I'll write it out. There should be no log here. No log. Okay, so once we simplify this, we get that the zeta regularized determinant is equal to some constant times this expression that we had. And the constant comes from the fact that the expression above is involving the log. And so if we want to eliminate the logs that end up on both sides, we can only do this up to a scalar. So we have to solve for this scalar. And so to solve for that C, that mysterious C, we just have to use asymptotics. So we look at, the zeta regularized determinant, we look at it using contour integrals. And using contour integrals and looking at lambda going to minus infinity, I'm able to get some asymptotics of this. And then I want to do the same thing on the other side. Again, I can consider like y1 and y2 are solutions, and you can think about them as having a parameter lambda. And so I also want to consider this side as lambda goes to minus infinity and look at the asymptotics. They should match up in their highest order term, and that tells me that C should just be equal to 1. So that's the generalized version there. And so we want to put it in context of the operator we really care about, which is A. And so if we consider specifically the operator A, we get this generalized Gelfand-Yaglom formula, which tells me the zeta regularized determinant of A is equal to this expression involving the derivative of QC with respect to Q and its derivative. Okay. And then lastly, we kind of had been writing these Gelfand-Yaglom type formulas in terms of the derivatives of the action functional. So I want to do that. I'm taking derivatives with respect to these parameters B1 and B2, and I get this very nice looking formula. And so this formula looks a lot like the discrete one we had in terms of A tilde n when we were considering the specializations. We still have the derivatives of F1 and F2 in the numerator, and then the denominator here looks like the determinant of the operator. Here I do have this m tagging along, which is fine. And so where are we at? So after we did that, you have to notice, I noticed two things kind of. We had these two really similar equations. So the first one was the derivatives of the action at the critical point were equal to, the derivatives of these functions over the limit of this determinant of this discrete operator, where we kind of reasoned that the limit here was finite and existed well defined with an asterisk. And then we had something very similar for A, and this was in the continuous setting. The only thing different was we had this M. We also had this hope kind of when we went into the discrete land, we had this hope that the limit of the determinant of the discrete operator should equal the zeta regularization of the regular operator. So we wanted, A tilde, the determinants of A tilde to kind of match up when we looked at the continuum limit. So we might suspect that the zeta regularization of A tilde, or the zeta regularized determinant of A tilde was equal to M times the zeta regularized determinant of A. If this was true, then I could just plug it into this second formula here, and I get that nice generalized Gelfand-Yaglom formula I want in the continuous setting. and this is just like this, I wholeheartedly believe this is true, but there's always been this issue, this underlying issue as we were working on all this stuff with the Zeta regularization of A tilde is funny. So we wanted this formula. We didn't quite have it, but we actually had it in the discrete case. With an asterisk. We have this in the discrete case. The asterisk always means an alternating minus sign. So the determinants of the discrete operators an and a tilde n satisfy the following relation. So the determinant of an tilde is equal to alternating sign m, the determinant of an. And this alternating sign, you're like, at first you're like, oh no, another alternating sign. But it's actually quite nice, because if you naively plug this into the discrete generalized Gelfand-Yaglom formula we previously had, the two alternating signs cancel. And so the discrete, like even in the discrete case, you don't have this weird sign issue. And a bit of a side note is that the sign issue was the first thing we noticed when the very first thing I did when I started working on this was trying to compute the Zeta regularized determinant of A tilde. And what we noticed was you could compute it a few different ways, and like you might end up with a different sign in front of it or a different phase. And this was really weird, but it seems to be related to the fact that it was a first order operator, so that there's some choice of phase when you choose a branch cut if you're actually taking these Zeta regularized determinants. And so the fact that this alternating sign kind of showed up for A tilde, your first order operator, but goes away when you consider A, your nice second order operator, sort of made sense in that context. And so, okay, I wrote this out, and I'm saying I've said this discrete operator an, but I haven't defined it. So I'll define it real quick. And I'll just define it with an example. So an is the discrete Laplacian operator, basically, with the potential. But you have the twos along. And of course, this is the case where epsilon is equal to 1. And the theorem's obvious once you observe that m times an is equal to this tridiagonal matrix we had previously for A tilde n. And once you have that, it's obvious. You get like a extra m from the dimensions of the matrix, and that's where this m comes from. So that was the discrete version of an. We had to introduce this. And so since we introduced this discrete operator an, we were like, okay, well, we should know whether this converges or not. So we have the same result. The operator an weakly converges to the operator a. As before, the limit is well defined and finite. And like I said before, the alternating signs cancel. So this is truly well defined. There's no question on choosing a sign here or choosing a convention of n. And so, this should say determinant here. So this should say the limit of the determinant of an is equal to the following expression. And again, we just have this extra m floating around. But and to prove this, one has to be careful about epsilons. Because we have to, the previous expression of an just assumed epsilon is equal to 1. We have to reinsert these epsilons appropriately, which is, in the case of an, it's a little bit more nuanced on where you're inserting the epsilons. And yeah, we have the m, but this makes sense. So we have something nice going on here. So what do we want to do? We have the determinants of an and an tilde. They exist in the continuum limit. And then the operators themselves converge to a and a tilde respectively. So we want to define a different kind of regularization here. different from the Zeta regularization, but hopefully the same in terms of actual computation. So we define the lattice regularized determinants of A and A tilde by the following. So the regularized determinant of A is the limit of AN, the determinant of AN, and the lattice regularized determinant of A tilde is the limit of AN tilde, or the determinant of AN tilde. So exactly what you think, just a different regularization. And if you want convergence, like you have to be careful about epsilon, obviously. When you're doing it, you can't take the limit of the determinant of AN tilde when epsilon is equal to 1 and get a convergent thing. Well, okay, I think you actually can in a few circumstances, but those are novel. And so we see from everything kind of done previously that the lattice regularized determinant of A is equal to the zeta regularized determinant of A. So these are the same in value, but very different in how you compute them. So on the zeta regularized case, the usual thing you do is you have to analytically continue the function and you have to take the appropriate contour integral. But in the case of the limit of, or the lattice regularization, you just have a finite matrix, and you, depending on the system, you're going to have to look at the recursive system is the easiest way to compute the determinant of it. And then you'll get some nice convergence. And so that's kind of the essence of what we did, the bulk of what I did, I guess. And there's a few things that should be said after the fact. The first is we wanted and never got that the lattice regularization of A tilde is equal to the zeta regularization of A tilde. I suspect this is true, but right now I don't have a good way of computing the zeta regularized determinant of A tilde or a Gelfand-Yaglom type formula. So you can kind of get away with not explicitly computing the zeta regularization if you can find that generalized Gelfand-Yaglom type formula. But I don't quite know how to do that for that first order operator. The second thing that's worth thinking more deeply about is something's going on kind of funny in the case of mixed second derivatives of H. So this probably warrants more investigation. We had those mixed terms and that product appear. I'm not sure what happens to the product if you want to consider convergence of the operator A tilde n, but I think it's worth looking at what happens and being careful about epsilons there, because I don't know, maybe you'll find something interesting. And also, I think this is a pro of the discrete version of the formula, because in the discrete generalized Gelfand-Yaglom formula, it really works for a whole lot more Hamiltonians than previous. So if we use that discrete case, you can really use any twice differentiable Hamiltonian you want, whereas any Gelfand-Yaglom type formula before, you had to have a Hamiltonian that looked like p squared plus v. And so that was really limiting in that sense. So this discrete formula kind of will inspire, hopefully, a more general version that works for a more broad class of Hamiltonians here. And then that's all I had to say. So I just want to say thanks for listening, and also if people have questions, I'd love to try and answer them.
Thank you. So, questions? Okay, so may I ask the question then? So can you say a few words about what goes wrong with the zeta regularization of the determinant, or it's a long story?
It's not that long, I don't think. So a few things that happen is even like if you even have a nice operator, in the case of the second order operator, you have a discrete spectrum that is that has some minimum. And in the case of the first order operator, your spectrum is still discrete, but it can go off in both directions at infinity. So this is manageable to deal with, but, well, at least I think it should be. But the other thing that happens is as you take this contour integral carefully, you don't have the you don't have the convergence of these integrals that you do. So I wonder, coming back to it, if you could be super careful to get these integrals to actually converge, but a lot of them are very poorly behaved and don't have the convergence that you get in the second order operator case. I think that's, and then the last thing I mentioned is that depending on where you choose your branch cut to be, and you have, depending on where you choose your branch cut to be, now you will actually change the phase of the value that you get. So there's something weird going on there that picking a branch cut will change the value of the determinant.
But in general, does this zeta regularization in principle can be applied to first order differential equations, differential operators, or this is?
I think so. I think somebody who should be like, I hope an expert in this knows like how you can get around this, but we were like at the beginning, we just were so confused about it and we're having so much trouble that we had to step back from this. And we were, I mean, the person that I know that knows these the best is probably Takajan. And he talked about the phase cut, but I think for the rest of it, I would need somebody like him to be able to compute these to feel confident that the answer we were getting was actually the right answer.
Yeah, but kind of lattice regularization seems to be more fundamental, right?
Yeah,
It
seems to be more natural thing to do.
Okay, thank you. Any more questions at this point? Okay, so let's thank Meredith for the wonderful talk. See you all next week. Thank you. Bye.